had missed some information there. I'm very sorry about that, but I had this ladder, a ladder that was up against the wall like this, and I gave you the height of the ladder, or rather the length of the ladder. That ladder was 10 meters, but I didn't give you this distance, which you also needed. This distance was 8 meters. Test, test, test. All right. Um, so I'm sorry about that, but you do need that information for that question. Did y'all get a chance to do question 1 and 3 over the weekend? No? Some of you? Maybe? No? Okay, try to do them this week, okay, so that next week you're not sort of overwhelmed with other things. I know you have a lot of stuff going on this week too, but try to do those questions before the test. That way you can focus more on your other classes and also on the actual, the, the in-class exam that we'll have. Uh, Today I want to wrap up, or maybe wrap up those other 3 questions, and you'll find that they're similar to uh, your other take-home questions. There's one that's very similar, and then we'll do another that's similar to the latter problem. A little bit different, but a little bit similar too. So hopefully you can hobble together those 3 different problems and do well, or those, I think we have 4 different problems, and be able to do the take-home test pretty well. Remember, you can use whatever resources. I don't think you'll find those particular problems. I just made them up, so you won't find those particular problems on the internet. Hey, Lazarus. But you can find some that are similar to that. Let's see. I also sent out the optics notes, which will be starting probably on Wednesday. I want to step through just the procedure that we had here. So I had this ladder that was standing up against this wall. Your first step is just to label all the forces. So we had 2 forces up here. The normal force is perpendicular to the surface. The frictional force opposes the direction of the motion, which is going to be directly upward. We had the weight, which acts at the center of mass. And then we also had down here the normal force and the frictional force. Again, the normal force is uh, perpendicular to the surface, so directly upwards, and then the frictional force is directly to the right. And then the big part of these problems is writing your equations correctly. We always start with our sum of the forces in the x and the y. Those are going to equal 0. And then you have to sum your torques, because the problem in these problems is that you have more than 2 unknowns. And so if you have more than 2 unknowns, you need more than 2 equations. So while these are independent equations, you need a third independent equation. And you can draw, or you can write the sum of the torques is equal to 0, because since this object is in equilibrium, the sum of the forces has to equal 0, and the sum of the torques have to equal 0. So you can write, well, you can write any number of equations for the sum of the torques, because since this object is in equilibrium, it's not rotating, it doesn't matter where you choose the axis of rotation. And so that's sort of the trick with these, is choosing the right axis of rotation. You can choose your axis of rotation anywhere, but you want to choose your axis of rotation where you get rid of one of your unknown variables. So for example, here we didn't know FSW or FNW, so we can choose this as our axis of rotation, and then those 2 forces provide no torque about that axis of rotation. All right, so that's sort of the general procedure. Once you get those 3 equations, we actually wrote 4 equations here, but you should really only need 3 equations to solve for 3 unknowns. Once you get those 3 equations, it becomes algebra then, solving a system of equations. And that requires, depending on the problem, requires a certain amount of substitution of one equation into another. All right? No really new material with this. It's really just sort of a new procedure where we're combining the sum of the forces and the sum of the torques. You want to do another problem? All right. This one's similar to one of your homework problems, or one of your take-home problems. I have this bar. It is 100 kilograms, has a length of 10 meters. The center of gravity is at the midpoint for just the bar, that is, and it's suspended by 2 cables. One, the angle is given, the one over here, and the other one, we don't know the angle, but I want to know the angle. So there's 3 things I want to know here: the tension in this cable, the tension in this cable, and this angle theta. So I have 3 unknowns, so I know I'm going to need at least 3 equations, but I'll actually write 4 equations for it. First thing we do is what? Right, just label all your forces. So similar to what we've done before, uh, I have this force. I'll call this FTL, the tension on the left side. And then this one, I don't know, what do you want to call it? FTR, how about that? Yeah, that sounds good. And then I have two more forces. I have the weight of the object, FW, is right here. And then I also have this additional force. I'm just going to call this F. Right? I have FW, that's the weight of the bar. It tells me the bar is 100 kilograms, so FW will be 1,000 newtons, and F will be 100 newtons, because I have that 10 kilogram object. So I'm going to go and write that up here, that FW, oh, it's a lot more outside. Okay, so FW is 100 times 10, or 1,000 newtons, and then F is 10 times 10, or 100 newtons. All right? I'm going to first write the sum of the forces in the x and the y. Sum of the forces in the x. And what I'm going to do here is take the components of these forces. So I didn't have to do this before because all the forces are either straight up or straight down or to the left or right. But I know that this force, the component of FTL, is FTL cosine theta. And then this force is FTL sine theta. So just take the x and y components of that force. And then over here I have FTR cosine of 60 and FTR sine of 60. So now I have all my forces either on the x or y axis. Some of the forces in the x then will be FTR cosine 60 minus FTL cosine theta, and that'll be equal to 0. Why don't you go ahead and do the sum of the forces in the y. Just take a half a minute or so. Start writing out the sum of the forces in the y direction. Looks like I have maybe 4 different forces that are in the y direction. Should look something like this. FTL sine theta, that's in the positive y direction. FTR sine 60, that's positive y direction. And then minus F minus FW, which is in the negative y direction. Now I'm going to write two equations for the torques. Where should I choose my axes of rotation for these two equations, where I say the sum of the torques equals 0? For the I'm going to choose my axis of rotation to be here, and I'm going to choose my axis of rotation to be here. This object isn't actually rotating around either of those axes because it's not rotating at all, but because I know the sum of the torques has to be equal to 0, I can choose whatever axis I want. Notice that I'm not going to choose about this axis because I already know what this force is, so I don't need to eliminate that force from my equations. Likewise, I'm not going to choose it about this axis, though I could if I wanted, but it doesn't really help me that much to do that. So I'm going to say the sum of the torques with my axis on the right is equal to, let's label some of our distances here. So I know that this distance from the problem is 3 meters. This distance is 5 meters because the force weight acts at the center of mass and it has a length of 10 meters. All right, so my sum of the forces with the axis about this point will be the force F times 7 meters plus the force weight times 5 meters. Notice that I've let those two be positive Because if I imagine this moment arm, these two forces are going to cause a counterclockwise rotation. So they have positive torques. And then I have some clockwise torques. Or no, I just have one, it looks like. Minus FTL times 10 times sine of theta. And that's equal to 0. Right, so that's my sum of the torques on the right side. I'm going to go back and circle all those things that are unknown at this point. So my theta is unknown, FTL, FTR, FTL, FTR, theta, and then I have FTL and theta right here. So I could just go with these three equations, and I could solve these three equations, but I'm going to go ahead and write a fourth equation as well. Right, because if I have three independent equations, I can solve for three independent unknowns. But let's go ahead and write a fourth equation as well. And I'll write it with the sum of the torques with the axis on the left. So now, instead of having my axis at the right end, my axis of rotation will be down here. I'll take a second and just sort of start writing out the torques with the axis about that point. Looks like I'm going to have three different forces that cause a torque. I have this force, and then FTR. Think about which of those provide positive or negative torques, which cause clockwise or counterclockwise motion. You'll need to know the moment arms for each of those forces, and then make sure you get the angles correct. I'll give you a little head start, then I'll start writing it down. This is a really nice equation. Why is this nice? It only has one unknown. In fact, if I had my wits about me, I would have just done this one first, because if I choose this one as my axis of rotation, it gets rid of not only the tension, FTL, but also the at angle theta. So both of those unknown variables are left out of this equation. So now I can solve this equation for FTR. If I solve this for FTR, it's going to be, let's see, FW is 100, so it's going to be 100 times 3 plus 1,000 times 5 divided by 10 sine 60. If you do that, you don't have to do it, but it's equal to 543 newtons. I'm going to tend to keep more significant figures than I need to for these problems, because as you're solving by substitution, just keep your number of sig figs more than you need until you get to the end. Yeah. Where did I get 10? Oh, 10. I think this is the 10. Right here? Yeah, so I get that 10. Remember, torque is equal to FR sine theta. And that's going to be my distance r. So here I'm the distance to FTR. 10 is the distance from this axis of rotation down to where that force is applied. It's the moment arm. It's this r value. Right, so for each torque, you need to find the force, where it's applied, the distance from the axis of rotation, and then also the angle theta. Or I could think about it in this way, as the force is this y component, which is FTR sine 60, times the distance. And then this y component is perpendicular. All right. That's really what I'm doing when I find the torque, is I'm finding the component of this force that's perpendicular to the moment arm. Does that answer your question? Yeah. All right. Okay, so now I know FTR. That's one part. Now I just want to be able to figure out, well, gosh, what are some of the other variables? Um, you might do this a little bit differently, but I started here, and I solved this for FTL. Yeah, let's see. Looks like maybe I made a mistake in my notes. Did I do that equation right? Is that equation? Yeah, I had a mistake in my notes. What do you get? 12? 612. You should always use degrees. All right. It looks like I had a mistake here. Let me fix it right quick. All right. So now I want to, I'm going to solve this other equation for FTL. And if I solve this for FTL, again, you might do this slightly differently. But if I solve this for FTL, I get FTL is equal to 570 over sine theta. Right? And then once I get that, I can plug this in for FTL. I took it up here and substituted it in for FTL there. And then I can solve for theta. You'll follow me on this? Because if I come up here, I can solve this for FTL. I get FTL in terms of theta. And then up here, since I know FTR now, if I replace this with something in terms of theta, then I have an equation with just one unknown. So let's see. Now I'm going to take this equation and make that substitution. It's going to look like this. I have FTR, which is now 612, minus, or times cosine 60. Minus 570 over sine theta. That's just making that substitution for FTL times cosine theta equals 0. So now I just want to solve for theta. Cosine theta over sine theta, what's that equal to? It's a cotangent, right? I'm going to do it as 1 over tan. So I'll rewrite this as 612 cosine 60 minus 570 over tan theta equal to 0. Where I substituted tan theta equals sine over cosine. You could do cotan. I don't have a cotan function on my calculator there, so that's why I did tangent. And then I solved this for theta. And I found theta to be equal to 64.5. So that's part of the answer. So now I know FTL and I know theta. I can go back up into any one of those equations that I have and solve for FTL. I know FTR and I know theta. So, well, I'll just take this one. This one's the easiest. I know FTL is 570 over sine theta. So FTL is 570 over sine of 64.5. And that's equal to 631. All right, so that's it. I have FTL, I have theta, and I have FTR. For FTL, oh shoot, I'm sorry. What is Does anybody know what it is? I had a mistake because I carried over my number. Let me show you. So here I'm solving for FTL from this equation right here. So FTL is equal to FTR cosine 60 over cosine theta. Wait, no, I'm sorry. Shoot, I'm sorry. No. Sorry, folks. I'm actually going from this equation. Well, it should have worked out right. So I have FTL is equal to 100 times 7, that's 7,000, or 700 rather, plus 5 times 1,000, that's 5,000, divided by 10 sine theta, which is going to be 570 over sine theta. Yeah, that's right. Okay. So I'm solving this equation for FTL so that I can get something in FTL in terms of theta. So then I can take this and plug it back in up here. So I remove one of those unknown variables. Does that answer your question, Sydney? Yeah. All right. The algebra is sort of really where you get bogged down, but you sort of have to be very methodical about it. Write out your equations very clearly. Make sure that you know what's known and what's unknown, how many unknown variables you have in each equation, and then set about substituting equations or maybe finding an equation that only has one unknown variable and solving for that. And then that greatly simplifies your method there. All right? Okay, let's do another one. You have one that's very similar to this in your take-home, but it's a little bit different one. This next example is also similar to that unworked problem, hopefully, the second problem, I think. All right, so here I have a 10 kilogram plank. It has a 5 kilogram mass that's 0.3 meters from the end, from the left end. So I'm going to go ahead and start labeling some of my forces. I have a force that's here. I'll call that FB. I have a weight that's going to be right here at the center. I'll call this FW. Then I have a normal force. Be careful here. Your normal force is perpendicular to that. Actually, no, I'm sorry, not like that. Your normal force is perpendicular, not to the plank, but to the pivot there. So my normal force looks like that. And then I also have a force here. I think that's all the forces. Is that all the forces I have on this? I think so. Yeah. These are kind of nice because all the forces are either up or down. So when I do the sum of the forces in the x direction, I won't have any forces in that. I'll only have some of the forces in the y direction. But then I'll need to choose two torque equations in order to give me a set of three independent equations. All right. I know that this angle is 70 degrees. I think in your take-home, in a similar problem, I give you this, but I don't tell you what the angle is. You have to find the angle. If this angle is 70 degrees, that means that this angle is also 70 degrees. This angle is 70 degrees. This angle is 70 degrees. And this angle is 70 degrees. So all those angles are equal. I also want to label my moment arms, or my distances rather. Since the board is 6 meters long, this distance to the weight is 3 meters. I'm told that this distance is 0.3 meters. It's right here, 0.3 meters from the left end. And the pivot is 2 meters from the left end. So this distance is 2 meters. Now I want to write my equation. So I'm going to do the sum of the forces and then the sum of the torques. Some of the forces are easy. Some of the forces in the x direction, there are none, so I'll just write it like that. Some of the forces in the y is going to be Fn plus F minus Fb minus Fw. I'm going to go ahead and write my unknowns here. What do I not know here? I don't know Fn. I think that's it. Is that right? Put my only unknown. I know the weight of the board. It's 100 newtons. I know Fb. Oh yeah, I don't know F either. Okay, so I do have two unknowns there. I have some choices with the torques. Let me think, what would you choose for the torques? I'm going to need to write two equations. Where am I going to choose my pivot points? I need to choose two pivot points here in order to write two equations for the torques. Hopefully those two torque equations will have some of my unknown variables eliminated. So where's my first torque going to be rotating around? Where's my first axis of rotation? Let's do it at the pivot, right? Because I don't know the normal force. So if I do it at the pivot right here, then it'll eliminate this normal force. And so I won't have to worry about that normal force mucking up that equation. So I'll do the sum of the torques about the pivot. Let's see. So I have at the pivot, I have three different torques. I have the torque due to this force, and this force. Some of them are going to give clockwise, some will give counterclockwise. Let's see, let's start with this force. Clockwise or counterclockwise? All right, that's counterclockwise. So this will be positive. This will be a negative torque. And this one is, what is this? Positive or negative? And that's counterclockwise, right? So that's positive. So let's start with F up here. I have F times the distance, which is going to be, do I know that distance? It is 1 meter from the right end? Okay, so this distance is 1 meter. Let's see, so that means this distance is 2 meters. What's that? This would be 3 meters? 2 meters. Yeah, you're right. So yeah, this distance here is 3 meters. Thank you. All right, so it's going to be F times 3 meters. Let me double check that. Is that right? You agree with that? That 3 meters? So I know that the distance from here to the middle is 3 meters. This is 1 meter over. And this is 2 meters from the left end. Yeah, that is right. Good. So that's 3 meters. Y'all follow that? Just draw your picture out. Make sure you label all your distances. It'll become clear, I hope, on your test. So that's 3 meters plus, or excuse me. Now I need to put in the angle. So the angle here is going to be sine of 70 degrees. I'll do my force weight minus my weight. This distance from here to here is what? That's going to be 1 meter times 1 meter times sine of 70. And now I also need to include this FB right here. That's a positive torque, so it's plus FB times, what is that, 1.7? Is that right? Times 1.7 times sine of 70. And then that's all equal to 0. All right, so that's one of my equations. Let's find my unknowns here. I don't know F. I think that's it, right? Because I know FB. That's my only unknown there. So that's really nice. I can just solve that equation, and then I'll have F. I guess I could just stop right there, because I'm looking for F. I'm looking for Fn. So yeah, I could just stop right there and find those. Is that right? Yeah. I could stop right there and solve for F, and then plug that in and find Fn. This one's pretty straightforward because I know that angle. Uh, so solve this for F. I'm not going to step through the algebra here because it's just solving equations with one unknown. So I solve this for F, and then I also solve, then I plug that in and I solve for Fn. The one on your take home is a little more complicated than this because you don't know the angle, but it's a very similar problem. Okay with these? Any questions about this one in particular? Are you excited about it? No? Okay. All right, let's do the last one, the fourth one. It's a little more difficult, but it's kind of similar to the ladder problem that you had. In this one, you have a sandwich board sign. Oh, by the way, when you get your answers on any of these, if I solve for F and I solve for Fn, a good way to check your answers is to just take your known values now that you've found here and go back into each of these equations that you've written and make sure that they satisfy those equations to make sure that you haven't made a mistake. Ainsley? I did, but I had made a mistake in my notes, and so I don't know what they are right off. Okay? We can do it right quick if y'all want. You want to get the answers right quick? All right, so we can solve this for F. I get F is equal to FW, which was 100 newtons, times 1 times sine of 70, minus FB. FB is 50 newtons, times 1 times sine of 70, or times 1.7 sine of 70. And then I'm looking for F, so I divide all that by 3 sine of 70. My sine 70 cancels, so I get 100 minus 50 times 1.7, what is that, 85? 85 divided by 3, so that's 5 newtons. So F is equal to 5 newtons, and then I can plug that back in up here and solve it for Fn. I get Fn is equal to Fb plus Fw minus F. Fb was 50. Fw was 100 minus F, which I now know is 5, so that's 145 newtons. So those are the right answers. F is 5 newtons, and then Fn is 145 newtons. All right? Turns out that the angle doesn't matter, that it cancels out. So it doesn't matter that the angle is 70 degrees. Angle could be whatever. So let's try this sandwich board sign. Here I have 2 uniform boards, and each has a mass of 4 kilograms, and they're connected on the ends by a frictionless hinge. So there's a hinge right here where they're connected. And then I have a chain that connects the 2 boards here. At the base, it's 1.1 meters, and the maximum height is 1.3 meters. First thing we want to do is just figure out some distances here. So I'm just going to draw a triangle. This is the triangle that's just half of this sandwich board. It allowed me to get some distances. It has a distance down here of 0.55 meters. and a distance over here of 1.3 meters. Now, if I think about the chain up here also, this distance is 0.5 meters. So the total distance is 1.3 meters, but this distance is just 0.5 meters. I can find this angle. I'll call it theta. Theta is equal to the inverse tan of 1.3 over 0.55. That's 67 degrees. And then I can also find this distance, which I'll need on the hypotenuse. Is going to be the square root of 0.55 squared. That distance is 1.4 meters. And then further, I can find this distance, which I'll need when I'm writing my torques. I'll write this triangle up here. It looks like this. 0.5, an angle of 67 degrees. And I want to know the hypotenuse. So let's see, I have the opposite side. I'm looking for the hypotenuse. Which trig function will I use? You could do that. What would that be? I've already used the sine function. I'll just do that. But you could do that. So I could say sine of 67 is 0.5 over the hypotenuse. And so that distance, I'll call it h, is going to be 0.5 over sine 67, which is 0.54. All right, so just some trig you need to get to find the angles and the various distances for the forces and where they're applied. Now let's write the forces. I have a tension here, Ft. That tension will be the same on this side, so it's mirrored. I have a normal force here, Fn and Fn. I have a weight, Fw and Fw. And then I also have the hinges. The hinges are going to exert forces on one another. I have a force due to a hinge right here. So this sandwich, this side, is leaning up against the surface of that hinge, and that hinge exerts a force that's perpendicular in that direction. So it's a lot like the ladder problem. And then I have also the hinge over here. If I want to find first the normal force, which I'll need to know the normal force, that's going to be fairly straightforward because I know the weights of these two planks, and I know the normal forces are also in the y direction, and all these other forces are in the x direction. So if I want to find the normal force, I just say the sum of the forces in the y direction. So let's go ahead and do that. The sum of the forces in the y direction are going to be Fn plus Fn minus Fw minus Fw. That's all equal to 0. So 2Fn is equal to 2Fw. 2's cancel. So the normal force on one side is just equal to the weight. And the weight is 4 kilograms times G, which is going to be 40 newtons. Right? But now I also need to find the tension in the chain, and I can't do that here. I mean, you could say, well, gosh, you know that some of the forces in the x direction are going to cancel out as well, but I don't know the force in the hinge, so I can't do the same thing with to find the tension. So I have to determine what are my equations for the torques on one side. So what I'm going to do now is just take one side of this sandwich board. Like say I'll just take the left-hand side of this, and I'll say that the torques all about that board are going to be equal to 0. So I'm just going to redraw this. I have the hinge, FH, FT, FW, Fn. This is all acting about this board right here. I'm going to choose first my torque to be about the hinge. So I'm going to let my axis of rotation be right here. Let's see, this should be actually not the hinge, but the FT. So all I've done is just redrawn my sandwich board, half of it, and I have it looks like this. If you notice, this is very, very similar to that third problem on your take-home test. It's almost identical. All right, so now I want to find out what is the tension. If I write the sum of the torques about the hinge, it's going to look like this. I'll have Ft times 0.54. I'll show you where that comes from in just a second. Times sine of theta is 67 plus Fw times 0.7 times sine of phi. It's a different angle from theta. I'll show you where it is as soon as I get written here. Minus Fn times 1.4 sine of phi. That's all equal to 0. All right, so I'm taking my axis of rotation about this point. So my first torque, this force causes a counterclockwise rotation. This distance is the same as this distance, so it's going to be 0.54, which we found up top there. So that's where the 0.54, and then the angle theta will be this angle theta, which is the same as this angle theta. So it's going to be 67 degrees. And here I have Fw. Fw is this force. 0.7 is the distance from here to here. We found that this total distance was 1.4 meters, so it's going to be half that because the weight is at the center of mass. And then the sine of phi is this angle right here. So if I know this angle is 67 degrees, this angle is going to be 90 minus that. So the angle phi, where theta is 67, the angle phi will be 90 minus 67, which is, 23 degrees. Okay? So I'm looking at the weight here, and I want to know this angle, which is going to be 23 degrees. And then finally, the Fn, that causes a clockwise torque. The distance is, so it's negative. The distance is 1.4 meters. That's that hypotenuse of that big triangle times the sine of the angle phi, which is this angle, which is the same as that we had there, which is our angle phi. A lot of geometry in these problems and a lot of trigonometry as well. Knowing where your angles are and knowing how to use the trigonometry to find those various things. All right, so that's our sum of our torques. We don't know the tension, and we don't know the normal. No, we do our normal force, actually. Yeah, so that's all. We only have one unknown in that problem, so we can solve for Ft. So our Ft will equal to, let's see, negative of a force weight, that's 40 newtons, times 0.7 times sine of 23, plus our normal force, which is also 40 newtons, times 1.4 times sine of 23, and then divided by 0.54 sine theta, 0.54 sine of 67. That's equal to 22 newtons. So that's our tension in the chain. Ugh, these are giving me a headache. Are these giving you a headache too? You just have to be very meticulous with this, okay? That's why I gave it as a take-home, because on a test, students always make problems with this, have sort of algebra mistakes. But if you have lots of time, you can sit down and just be very careful with your variables, be very careful with how you label your forces, and then solve those equations with by solving the system of equations. So that's part of it. I wanted to know the tension in the chain. Actually, I think that was all for the first part. I just wanted to know the tension in the chain. Okay? You with me on this? Is this helping you for your take home? I think it will help you. Your problems are very similar to this. So when you sit down with your take home, sit down with these problems as well, and that'll help you guide you through how to solve these problems. All right, the last problem, part B, was a little more complicated. In that part, I had now not just tension, but I also have a frictional force. So we'll wrap up with this problem. I'm going to redraw my plank there, just one half the side. Redraw my forces. I still have all the same forces, Fn, Fw, Ft, and, oh, I removed the chain, right. So I don't have Ft anymore. Instead, I have a frictional force. There's my Fh. And then I have a frictional force, Fs, that's holding this in place. My normal force is still the same because the forces don't have any additional forces in the x direction. So my normal force is still 40 newtons. My weight is still 40 newtons. But my frictional force will be different. So this one works out actually very similarly. I'm going to write the sum of the torques about the hinge because I don't know the force on the hinge, and so I let my axis of rotation be about this point, recognizing that this angle is 67 degrees, this angle is 23 degrees, and this angle is also 23 degrees. So the sum of the torques about the hinge are going to be the weight, which causes a counterclockwise torque, times 0.7 times sine of 23 minus Fn times the distance, the height, or the length of that board, which is 1.4 meters, times sine of 23, plus Fs times 1.4 times sine of 67. And that's going to all equal to 0. I can solve for Fs. I'll let you do this on your own. But Fs works out to be 12 newtons. And then if I want to find the coefficient of friction, is really what I'm looking for. Mu s is Fs over Fn. Remember, we had this expression for Fs was mu s Fn. So it's going to be 12 over 40 is 0.3. Okay? I know that's very tedious, okay, and that's why we don't spend a whole lot of time on it and why it's part of the take-home. It's tedious. It's very tedious. It is kind of tedious. So try it out on the take-home. Let me know if you have issues. Remember, you can work together on this if you like. You can use other resources. You can everything's fair game for the take-home. But just make sure that I would try to do it in the next few days while this is still sort of fresh. Any questions, y'all? Thanks for hanging in there. I know that's kind of dry. Not really. It's really just sort of algebra, trig, and geometry. Nothing really new as far as the physics. All right, we'll stop there. We'll finish up. We have